All right, here we go. Lesson 7.2, estimating mu. In this case here, we are looking to try to estimate the true mean. So we will be going from what we call the sample mean to the population mean, and then looking at what the confidence interval is for the mu, and finally looking at what is a necessary excuse me, finding a necessary n value given a certain confidence interval. All right, so like how many things, how many data points do I need to be confident of our mean? All right, so first of all, very similar to lesson 7.1 in that x hat is the best point estimate for mu. Looking at how do we establish this confidence interval where the standard deviation is not known. Okay. Well, there are several variables. I think the trickiest is this new one, which we would call E, the margin of error. And we'll get a formula for that in just a moment. And then there are requirements, as usual. The sample has to be a simple random sampling. The population has to be normally distributed, or n has to be greater than 30, or we can have a combination of things. That is, if we have, say, 20 items in our collection, in our samples, then, and it's somewhat normally distributed, then that's okay. We can still use the following formulas. All right, this is how we write out those confidence intervals with which help approximate mu. So again, there's the three formats just like last time. And here is the first formula of two formulas. This is the formula for our margin of error. I should write that up here. Margin of error for our sample mean. Notice it uses t, which is a distribution, very much like our normal distribution, but not quite. So this piece here is a little bit odd. More on that in just a moment. Again, depending on what confidence level you're at, then that is going to determine your alpha. Again, t represents the critical value that separates the significant from the non-significant in our distribution. And then t sub alpha divided by 2, that describes the right tail area. So that would be this little area right here. Okay? And here is the critical value t sub alpha over 2. One thing we need to pay attention to is degrees of freedom in our equations. In this case, n minus 1, so 1 less than the number of items is going to determine our degrees of freedom. If n equals 10 and x bar is 5, so the mean is 5, right, of these 10 samples, then our sum is going to be 50, right? 10 times 5. And the way this is explained in the textbook, and I think it does make good sense, if you have 10 items in this list, no matter what 9 of them are, yeah, let's say for some crazy reason they're all 0, right? Each one of them represents 0, dot, dot, dot. And I have all the way down to 9 of them. Then the 10th one is not free because I have to get a sum of 50. So the 10th one would then have to be 50. And if somebody said, okay, well, one of those is 100, well, then the last one would be negative 50. So we can always adjust the last item to kind of complement the others. So 9 of them are free, but one of them is frozen, so to speak. So we have 9 degrees of freedom is the way they describe this. If you are finding the final calculations, there are rounding rules which you must consider. Are you working with the original set, or are you working with the summary stats? That's going to differentiate how you round it. If it is the original data items, then you go +1 decimal value from what they gave you. Otherwise, you round to the same, whatever the summary stats are rounded to. All right, so here is the t. It's called a student t distribution sometimes, but I think more often than not, I'm seeing it show up as just a t distribution. All right, and this is close to the normal distribution, so let's take a look at it. So the green graph, you can see, is the upper on the middle, but then lower on the edges. That is our standard normal distribution. Our t distributions are typically, you can think of them as shorter, right? But notice when n is 3, so we only have 3 items, notice how it's above on the tails. And that's because if you take away this area here, you have to tack it on over here, okay? So there is your t distributions. Here is the formula for establishing t. T depends on x bar and mu divided by the standard deviation divided by the square root of n, the number of items. All right, and so this is a distribution of all the sample sizes n. Again, the degrees of freedom, we abbreviate that df, is n minus 1. There's a new table, or you can use technology. It's similar to the normal distribution, but wider as n increases. And as you can see, the mean is 0, t equals 0, just like z equals 0 in the normal mean. All right? Okay. Procedure for building the confidence interval for mu. First of all, make sure you go through the requirements. There is a simple random sample, and then we have a normal distribution, or n is 30, or that combination that we talked about. Theta is unknown. Our degrees of freedom are n minus 1. And then again, we're going to use table or technology to find that critical value. And finally, round. Once you find your margin of error, write the interval, and then round it appropriately. So here we go. First of all, finding our t value, which I round to the thousandths from the table. So the degrees of freedom in this example is 14 because n is 15. Our confidence level is 95. So 95, and then 5% is the alpha, because that's the complement. The area is half of that. So then taking those two values to the table gives me 2.145. So an example of this would be, pretend that n now, being 15, is the female births. And our average, our mean weight in that group is 30.9. Standard deviation is 2.9. So what is the confidence interval for a 95% level? All right, it is a normal distribution because these are weights, and we have a simple random sampling. That's how we selected the 15 female births, right? All right, there's two options. You can go to StatCrunch. This is option 1. Or calculate E, and that's what I'm doing here. So notice I plug in my t value, 2.145, that I got earlier. Take 2.9 divided by radical 15, and I get 1.6. Okay, finally go over to our chart here, and 30.9 minus 1.6. So there's the mean plus my error, or minus my error, and then the mean plus the error. And mu is between that. So then here's my confidence interval. Now StatCrunch will take you straight there as well. And I'll make a video of that and put that online. We are 95% confident that the limit of 29.3 and 32.5 contain mu, which means that if we collect more samples of 15, 95% of them should contain that value, that magical mu. Then we have ways to estimate the mean of the sample and the error using those upper limits, right? We either add or subtract them. So for example, here's my upper limits, right? If I add these two together and divide by 2, yes, that will then give me the average, right, that I had, which in this case would be 30.9. And then if I subtract them, find the difference, divide by 2, that's going to give me the error of the confidence interval that I've established. This example is more of a kind of a just notice. So here we have secondhand smoke, and the figure at right shows the 3 types of people: smokers, people exposed to smoke, and people who are not exposed. And it shows the amount of cotinine, I don't know how to pronounce that, in the body. But this is a substance which is produced by the body when exposed to nicotine. So you can see that there is an overlap region between these two. And the mean, the true mean, might be like the same for them. But we've got to be careful about how we make conclusions from here. We can informally talk about that, but later on in chapter 13, I think they mention more specifically how to do proper formal conclusions from this type of chart. But you can see that the 95% confidence interval overlaps between people exposed to smoke and people who have not been. All right. Then we can re-engineer. This is finding the sample size from an estimated mu, needed to estimate mu. Okay, so here's our formula for n. And notice we have our z-value times the standard deviation. So in this case, you've got to have the standard deviation. There are ways around that, more of that in just a moment. But divided by the error, square that result, and then you round up to the next larger whole number. Important. Notice this does not depend on the total population. It only gives us the sample size, irregardless. Make sure that you always round up. If standard deviation is unknown, you can do a couple things. You can do rule of thumb, which is the range divided by 4, or go to another study. Yes, and a similar study, it's got to be around the same stuff, and use the standard deviation they have. Again, when you finally should finish, make sure that you overestimate things, because you don't want the error to be smaller than or the number of items, either, to be less, because then that would mean that you would get a worse mu, right? So we got to make sure that we always overestimate in these cases. Example, let's say you have IQ scores of stat students, and you want to know, like, how many do I need to get so that I'm within 3 IQ points of the mu. And this is at a 95% confidence level. So start with a 95% confidence level. That takes us to 5%. That takes us to a z-chart. Remember those days of going to the z-chart? 1.96 from that standard deviation. All right. E is plus or minus 3. And then from another study, related study, this you have been given that. You can't go out and research it right now. But we get 15 is a standard deviation of students with IQ points in a stats class. Plug all those in, we can see that we need about 100 students, 97 specifically, to achieve that interval plus or minus 3 standard deviations. 3 IQ points, not 3 standard deviations. All right, and there we go. Hopefully you are able to finish 7.2. Best of luck. On to 7.3 next time.